In this episode, we're going to talk about design considerations in order to minimize leakage through installed geomembranes and even achieve zero leaks. In order to do that, we're going to first go over how to quantify your target performance or target allowable leakage level. In order to do that, we need to understand leakage statistics, and I'm also going to provide you with an equation for calculating the probability of exceeding your target leakage level. So we're going to talk about how to calculate leakage through geomembranes and how wrinkles affect geomembrane leakage performance. Then we're going to go into different lining systems for various project configurations and construction materials, including geosynthetics and earthen materials, and how all of those types of materials and layering systems actually affect electrical leak location methods. We will talk about ELL method selection and how to look at specific project details and configurations in order to advise on method selection. We will go over how to write method specifications for projects and also how construction water trapped in the leak detection layer can affect ALR compliance. So the target performance or target level of leakage is usually determined by what's called the ALR, or the allowable leakage rate. Some folks refer to it as the action leakage rate. So that's a level of leakage that if you exceed that amount, your site will not be permitted to operate, or it will cause some sort of regulatory action. Usually that you have to stop operations if you've already started and go and find where it's leaking and fix that before you can continue to operate. So it's really important to not exceed that ALR. I've seen zero leakage in some specifications, which some folks think is impossible to achieve. According to JP Giroux, all liners leak. We'll talk a little bit later about why he would make that claim. But I can tell you it's possible to install a geomembrane without holes in it or zero leaks. However, it's essential that any project that really cares about leakage, if you want that geomembrane to perform at all, you really need to use EL methods to reduce the risk of leakage in general and exceeding that ALR for your site. So in order to make sure that EL methods are going to be maximally effective, we need to understand the project-specific configuration and materials that affect the effectiveness of the EL methods. We also want to make sure that we are choosing the appropriate method for our project and that we have appropriate and thorough specifications for those methods. So how do we figure out how much leakage to expect from a typical project? In order to answer this question, a few years back, I went into leakage statistics from double-line facilities for thousands of double-line sites. So these statistics come from sites that are double-line facilities that have an ALR of actually 20 gallons per acre per day, which is 189 liters per hectare per day, because this chart is in SI units. So what I did is I took statistics from thousands of landfill cells and I plotted them on this histogram. And it turns out they make a really beautiful curve here. In fact, these are leakage statistics from sites where no ELL was applied or no known ELL was applied. So you can see that if the target is 189, which it is for these sites, you have a handful of sites that are exceeding that have problems. This chart is a histogram of leakage from sites that had the dipole method applied. So that's after the cover material placement. So you can see this x-axis is a lot different. So the target, again, is 189. You only have 2 sites that are exceeding that leakage rate. So I took the data from the first slide that I showed you, that histogram of number of sites and leakage rates, and I formatted them a little differently. So this is leakage rate on the x-axis and the percentage of sites that were exceeding that leakage rate plotted with the red squares here. And it turns out we make a really beautiful curve that can be modeled by an exponential function, which I named the probability function. So the blue diamonds there, this is a probability function that I'm going to give you the equation for, where if you know the leakage rate that's a target, it'll tell you the probability of exceeding that leakage rate, which is based on whatever ALR you specify and the mean of the data set for your leakage. So this exponential function here, I use the mean of the data set for the data shown in that histogram on the first slide. This is that same equation using that second set of data where the dipole method was applied. So again, it works on any data set regarding leakage, as long as you know the average leakage level of your data set. And you can enter your target ALR and it will tell you the percent probability of exceeding that based on actual leakage statistics of other similar sites. So this is that probability equation formatted as you would see it inside of an Excel spreadsheet. So you just need to know the average leakage value for the data set, and you enter in your ALR, and it yields the probability of exceeding that ALR. So this is when you have the most likely value for a data set. So if you know the average leakage for this type of project, you can use this equation. But what do you do if you don't have enough statistics or you don't know what that average leakage value is? Because again, the statistics that I showed you are only for a specific type of project, which would be, these were landfill cells in a state that requires an ALR of 20 gallons per acre per day. So it has really good CQA. And so it'd be extremely high quality primary geomembrane installation. So now we're going to go into the leakage equations so that you can figure out what type of leakage to expect on other projects. So first of all, we have 3 leakage equations we can use depending on the lining system and the condition of the installed geomembrane. We have the Bernoulli equation, which is applicable to free flow below the geomembrane. So this would be, for example, primary geomembrane on top of a free-flowing drainage layer, such as geocomposite or very porous gravel. But it doesn't have a low permeability layer right below the geomembrane. In other words, it's not a composite system. It's just a single geomembrane free-flowing. Then we have the Giroud equation for a geomembrane underlain by a low permeability layer, such as compacted clay or a GCL. However, you can only use this equation if you have pretty good contact with the underlying layer. If you have any kind of wrinkle or subgrade rut, you need to be using the row equation. So the row equation is for geomembranes underlain by a low permeability layer, but where the geomembrane is not in intimate contact with the underlying layer, also known as located on a wrinkle. So here's a diagram to help you understand the mechanics of the row equation. We have a geomembrane with a wrinkle on top of a thick, low permeable layer, probably compacted clay. And the row equation is assuming that the hole on the wrinkle is large enough that it can fill the wrinkle with fluid. You notice there's no r sub naught or radius of the hole in the equation. So the wrinkle is filled with fluid and it's free flowing through the low permeability layer, and it's also squeezing in between the interface between the geomembrane and the low permeability layer. So you have liquid flowing through the width of the wrinkle, the length of the wrinkle, and also squeezing out between the geomembrane and the subgrade just a little bit. The problem is that wrinkles don't disappear when they're covered, rather they're encapsulated. They get a little bit smaller, but they still remain there after they're covered. Also, locations where wrinkles tend to gather also tends to be a location where holes are more likely. So for example, the toe of a side slope, you have a lot of repairs there, and you also have a wrinkle that kind of gathers at the toe there. I've also seen locations where wrinkles get hit by dozers that are driving a little too close to the lining system. And the problem is that most ELL methods are not going to be effective on wrinkles. So in order to pick up a hole, we need intimate contact between the geomembrane and the subgrade. But the wrinkle keeps that intimate contact from happening, so it doesn't allow the electricity to go through the air in that wrinkle. And the problem is that a hole on a wrinkle results in 100 to 1,000 times more leakage than that same size hole in intimate contact with the underlying layer. In fact, according to J.P. Giroux, a geomembrane, when it exhibits wrinkles, it has a performance only slightly better than the performance of a low permeability soil liner alone, which is pretty incredible until you look at how much of the lined area can be covered by wrinkles. This is a photo of an installation, a geomembrane installation, where they took a photo from a blimp and then they put it in a CAD program and actually quantified how much of the liner was lifted off of the subgrade. In fact, it's not just a localized problems, but you can see this network of wrinkles. They're referred to as hydraulically connected wrinkles. So, for example, if you have a hole, let's say here in this wrinkle, it can get fluid and it can fill this whole network of wrinkles up with fluid. Here are some drawings that digitize the wrinkle extent as a function of time of day. So in the morning, you have a few scattered wrinkles that are not hydraulically connected. And then as the day goes on, as the sun comes out, as the liner heats up and expands, those wrinkles start to connect to each other. And then you get at the height of the day, probably 1 or 2 p.m. afternoon, you can have 20 to 30% of that lining system hydraulically connected and lifted off of the subgrade. The best way for us to understand the dynamics of geomembrane leakage is to actually measure leakage through the primary geomembrane of a double-line facility. This particular landfill was a 5 gallon per acre per day landfill cell. That was their ALR. They happened to be exceeding that. They were leaking about 20 to 30 gallons per acre per day. Several leak location companies weren't able to find the problem. This cell did have problems with isolation, so that affects method sensitivity. But regardless, when I came into this project, I suspected that the issue might be wrinkles or poor contact between the geomembrane and the underlying primary GCL. So they were actually measuring leakage every day. So we had really accurate records of how much it was leaking at what level of hydraulic head over the primary. So when I came into test, I asked that they leave a few inches of head over the primary so that it would kind of overcome any issues with wrinkles or poor contact conditions. So we did the test. We located, I think there were 8 or 9 leaks in total at these locations here that you see on the red dots. So after the survey, we were able to ascertain exactly how many holes, where, and how large, and at what level of head for each of those readings that were taken. And so we were able to really accurately quantify how much leakage should be attributed to each and every one of those holes. So the first thing that was done in this study is figure out, well, which equation should we be using for the holes that we found? There was only one hole that was really obviously in intimate contact with the subgrade. It was in the middle of the sheet. It was just a circular hole that was about 3/16 inch in diameter. But all of the other holes were located at the toe of the slope on these repair patches that were in basically at the intersection of the geomembranes coming together. You could see this is the side slope geomembrane, the textured, and the floor geomembrane was smooth. So it's right at the toe of the slope. And we wanted to know, should we use the Giroux equation or the row equation for this type of condition? So it turns out, when we did the calculations, that given all those holes where they were, if they had been in intimate contact, they should have collectively only have been leaking less than 1 gallon per acre per day. See this column 2 here? But it was actually leaking right around 30 gallons per acre per day. However, when we put those same holes using the row equation, we get up to what was actually measured. We got just under 30 gallons per acre per day. So even if you adjust one of the parameters for the Giroux equation for poor contact, it's still only gets up to less than 3 gallons per acre per day. So clearly those holes on those repair patches were not intimate contact. They should have been modeled as being on a wrinkle. When you look at column 5 here, which is column 1, which is the actual recorded daily leakage, minus the row equation, you look at what the residual leakage is, just under 5 gallons per acre per day, and this is pretty much spot on from what was measured after we repaired those holes. So going back to what these holes look like, I mean, this is a repair patch. This type of thing you see on nearly every geomembrane line installation. You never get perfect intimate contact right where these panels intersect. You always have some level of geomembrane lifting off the subgrade. So the point is that conservatively speaking, as a designer, you should be using the row equation rather than the Giroud equation when you're trying to project how much leakage to expect, because that geomembrane could easily be lifted just a little bit off of the underlying subgrade, and subsequently you're going to get a lot more leakage than if you assume it's an intimate contact and you use the Giroud equation. So going back to the equation for probability of exceeding a target leakage rate, we are after the mean of a data set. You can also think of it like the expected level of leakage. So how do we calculate the expected level of leakage? Well, we know that we should be applying the row equation to areas of poor contact. So we need to estimate how much of the lined area is going to have poor contact. And we also want to know what type of ELL technologies are being applied, and that will let us know how large the leaks are that are going to remain in the lining system and where they might be. So the first thing you need to start with is number of holes per acre or per hectare. And you can guess at this number. You can find statistics published. One source is down here at the bottom of this slide. It's a pretty old reference there. So older statistics tend to have many more leaks per acre than modern installations. So you have a leak rate, number of leaks per acre or per hectare. And then you need to assume that when you apply the electrical leak location, it's going to locate all the leaks that have good contact. So of those, in this example, 4 leaks per hectare, it's going to locate most of those because most of the lining system is going to have good contact. But a couple will remain somewhere where you don't have good contact. You can use the Giroud equation to calculate holes through leaks that are too small to detect with the ELL methods. But that leakage value is going to be negligible. When you have a small hole in intimate contact with the subgrade, there's very, very low level of leakage. So what you need to do is you need to use the row equation to calculate the leaks from those holes that were not detected by ELL. And in order to do that, you have to assume a certain percentage of area that's covered by wrinkles. So that's going to depend on the time of day that the liner was covered, the geomembrane type, and what I mean is, are you using conductive back geomembrane that enables leak detection on wrinkles? Are you using white geomembrane that actually reduces the prevalence of wrinkles? And things like field conditions, how it was placed. So you want to multiply the leaks per hectare by the wrinkle percentage to find the number of leaks per hectare remaining after ELL is applied. So I'm going to go through a design example that was published in 2015. So here are all the assumptions that went into my calculations. So I assumed a number of leaks per hectare. I assumed that the ELL would not detect leaks on wrinkles. I went to the literature to get basically percent of lined area that would be covered by wrinkles for typical geomembrane and white geomembrane. I also went into the literature for suggested wrinkle widths and lengths for typical installation. And then I'm assuming a hydraulic head of 0.3 meters or a foot because this is a landfill expansion cell. So this is what I came up with in terms of probabilities. So if you apply the dipole method only after cover material placement, you have a 6.6% probability of exceeding 20 GPAD and 50.7% of exceeding 5 GPAD. Again, these probabilities came from actual leakage statistics that I had. The numbers below on the chart for the other types of applications, this is where I use that equation. So the second row here, where you apply the ELL while the geomembrane is bare, and then again after cover material placement. So you're going to find not only the larger leaks that were caused during cover material placement, but also all of the really small insulation damages before the cover material goes down. So the probability of exceeding 20 GPAD, acceptably low. However, the probability of exceeding 5 GPAD, a little bit too high for my comfort level. However, if you apply some kind of wrinkle reduction strategy, such as using white geomembrane instead of the black geomembrane, then both of those probabilities go below 1. And following this logic, if you have conductive backed geomembrane, the probability of exceeding any leakage rate is essentially 0, because as long as everything's done properly in terms of applying the test, you won't have the issue with not being able to detect leaks on wrinkles because of that carbon backing the conductive back liner. So we know that leaks on wrinkles are a problem because they leak excessively. What can we do to control them? Well, we can have a maximum wrinkle height specification. We can control the time of day when the liner is covered. We can specify white geomembrane, so it limits that solar radiation so the geomembrane doesn't heat up as much, it doesn't lengthen as much, and you don't have the creation of so many wrinkles. You can also specify conductive back geomembrane, which it's virtually eliminating those wrinkles, so it enables the ELL methods to work in poor contact situations. The other thing you can do, which I do a lot because I test double-line landfills in a state that has a 20 GPAD ALR. So if you go to that table here, this is what I'm working with, this top row here. I'm only doing dipole method only. See how we're in the red? We have a really high chance of exceeding 20 GPAD. And we're only using the dipole method for the sites that I test at. So what do? I ask for lots of water when I test. So just like that case study that I mentioned where we were able to find leaks that other folks hadn't found because we asked for standing water above the geomembrane to overcome those poor contact conditions. You can also do that as well. So of these 4 boundary conditions, it's really easy for us to tell when we're testing if the medium above or below the geomembrane is not conductive enough. We know that immediately when we set up for our functionality test. We can tell visually if there's issues with survey area isolation, so that's something we can fix just with a visual inspection. The one thing that we're never really gonna know for 100% is if all the holes throughout the survey area have conductive medium in them, and I'm speaking of soil-covered survey areas. There might be a hole on a wrinkle somewhere that we're not aware of. So I really think this boundary condition number 2 is the most difficult one to achieve. That's really the wild card. So part of the problem is the types of cross sections that we're testing. Let's take a look at a very typical geomembrane line facility. This one happens to be for a landfill expansion. This is a double line landfill. And it has many layers. It has earthen layers and it has geosynthetic layers. So in this example, we have drainage material. This is a granular soil-based drainage material. We have geotextile. We have the primary geomembrane. We have GCL. We have secondary drainage material, secondary geocomposite, secondary geomembrane, and that low permeability soil. So there's so many layers to these systems. You might even have a triple line facility. But something like a geotextile or a geocomposite made of plastic that's not naturally conductive, we need to address that because the electricity needs to travel from the top layer through those geosynthetic layers, through the geomembrane to get to that underlying conductive layer. So what I want to do is break down all the different types of materials that we could be using in these lining systems that are going to affect the testing results. Let's talk about the different types of geosynthetic layers that we might have in our lining cross-section. We have geotextiles, geocomposites, and GCLs. So starting with geotextiles, the biggest issue is really just reducing or removing the contact through a whole location. It's typically not a problem as long as the geotextile is wet because it tends to wick moisture and hold on to it when it's kept covered. When it's exposed, like it's on top of a drainage layer, it dries out really quickly in the sun, and you need to add moisture if you're going to read voltage through that layer. However, a thicker geotextile is going to be harder to get water through. So the thicker the geotextile, the more of a problem it is. And no matter what, when you have a small hole, the geotextile is still going to make kind of like a bridge over the top of it and keep moisture out a little bit unless it's really, really wet or actively leaking. So a geocomposite, where we have a geotextile separated by a geonet core, the geonet core is really more of a problem than the geotextile. Geotextile wicks moisture and kind of holds onto it and is conductive when it's wet, but the geonet core is more of a plasticky product that doesn't wick moisture as much. So the geocomposite needs to be really wet, especially in order to detect damage caused before the placement of the geocomposite. So if it's not fully saturated, and I would say with standing water, you're only going to be able to find the damage that actually breaks the geocomposite, so the damage caused by cover material placement. So no matter what, having a geotextile or a geocomposite above your geomembrane is going to affect sensitivity. How much you can kind of overcome that reduction in sensitivity depends on how much standing water you can have above that lining system. Now, GCL, where you have two geotextiles separated by a clay layer, is not usually a problem, especially when it's placed on subgrade. The clay portion of the GCL is highly conductive and highly hydrophilic. So it will readily wick moisture not only from the subgrade, but from the air. So it's really only a problem if it's encapsulated, meaning that you have a primary geomembrane and a secondary geomembrane that's separated only by a GCL. If you deploy the secondary geomembrane and then the GCL on top of it, and then it's really arid, hot climate, it can bake out in the sun. So if you don't cover it with the primary geomembrane right away, it can definitely desiccate beyond the point where it will carry current. GCL coming out of the factory is typically at a moisture content that's conductive. This is something that's product specific. If you want to read more about this, there's a paper with a reference at the bottom of the slide here. But with all of the different types of GCL that I tested for that paper, I found that a lower moisture content for all the products that I tested was 8%. And I found that the products with the larger granular, larger grains of clay were less conductive. So they needed a little bit higher moisture content than the powdered type of bentonite. But again, this is something that's product specific. And if you have thicker geotextiles on either side of the clay layer, this could definitely affect it. Here's a chart showing the electrical conductivity of various natural materials that we work with. So salt water is highly conductive. Ice is not conductive enough for electricity. Clay is more conductive than a till, which is more conductive than a gravel or sand. And we can always add water to these materials to make them more conductive. Clay or prepared subgrade is always sufficiently conductive, especially if it's been moisture conditioned. We only need about 0.5% of moisture content for those types of materials to be conductive. So the only issue with something like a clay or just a till soil is surface desiccation when it's used as the cover material. So in hot and arid climates, we might need to irrigate the cover just a little bit to provide the electrical access for our probes to the top of that. Gravel and stone tends to need irrigation, especially if it's clean. Dirty stone kind of holds on to the moisture a little bit more. If you have large diameter clean stone, it's probably going to need to be watered immediately prior to the test. Sand is less conductive. It requires a higher moisture content, greater than about 6%. Concrete is very conductive with very little moisture content, and you can have issues with rebar, especially if the rebar doesn't have a coating on it. We've successfully tested through concrete with rebar in it, but when we find leaks and they cut out the concrete and they go through the rebar, we'll get false positive signals on the end of the rebar where it was cut off, because iron, when it oxidizes, it kicks off electrons, and that actually looks like a leak to us. So, so along those lines, anytime you have an exchange of electrons, you can get electrical noise or anomalies throughout the voltage field. So anything that's mineralogically rich or is chemically or biochemically active, it can create this noise throughout the survey area. What do I mean by that? Well, we'll get a voltage drop that's caused by the exchange of electrons, where normally we're looking for a voltage drop over a leak. So this is how things other than holes can create these, what we call false positives throughout the survey areas. Sometimes we need to dig it up to make sure. But for the most part, we can tell when something is caused by a feature other than a leak, especially if we're familiar with the materials throughout the area. Like, for example, if you have an LCRS trench with materials that are different than the rest of the cover material, we'll often get a little either voltage peak or voltage drop when we cross that trench. But then when we rotate 90 degrees and survey along the trench, we won't measure those same drops. So we have tools that can kind of tell us whether it's an anomaly or whether it's a leak, but sometimes we have to dig it up to make sure. Pure rainwater is not conductive, but it readily grabs ions from anything that it touches. So if you have really, really clean sand or gravel that only is touched by rainwater, that might not be conductive enough to survey. So we actually like dirty water or surface water. Something like brine is highly conductive. So if you have any isolation issues, it becomes way worse because you put in a current injector into the material, and then any little isolation breach it will readily find. If you have a less conductive material, it's more forgiving of those isolation issues. And also with the highly conductive material, you have very highly localized voltage drops. So it's just a little bit harder to find those leak signals. So when you have chemically or biologically active solution, it's just the same as having a biologically active or chemically active cover material or soil material. So it can be a problem not just for the noise that it creates, but it can actually react with the electrodes we use to measure voltage potential. And anytime you have this electrical noise, you introduce uncertainty to the results. So if we have a completely homogeneous survey area and cover material, then we'll have a very clean voltage map, and it really increases our confidence that any blip we see is coming from a leak and not from something else causing an anomaly. For covered geomembrane testing, most of the problems that we encounter are solved with the addition of water. Usually a good rainfall is sufficient. How much rainfall is sufficient? Well, the geomembrane should be forced to leak before testing, ideally immediately before testing. So if you don't get a sufficient rainfall, you're going to want to add enough water to that cover material to cause the geomembrane to leak. And what that's going to do is it's going to irrigate those dry geosynthetic layers, and it's going to overcome some of the poor contact issues that we've talked about, such as holes on wrinkles. Can there ever be too much water? Usually more is better. We always say just add more when in doubt. But the only time there can be too much water is when the applied water actually flows out of the survey area and causes an isolation breach. So if you look at this grading plan here, this is the testing area up here, and this is an 880 contour, this is an 870 contour. So any water that's applied to this testing area flows to the existing cell. So it's going to run off of the expansion cell. So unless you have something like a rain flap here, if you have a lot of water in the testing area, it's going to flow off and cause a grounding issue. So when we have a configuration like this and we can't control the water inside of the testing area, we'll suggest that it be watered, say, the afternoon before the test, and then let it sit overnight for that excess water to kind of drain out, and then we could test it first thing in the morning when it's still pretty nice and moist, but we don't have a lot of water actively flowing off. So speaking of flowing off the liner, I have seen that free draining slopes are going to reduce the detectability of a leak because on the floor area or an area with less of a slope, you can get water to kind of pool and slow down. If you have a free draining slope, something like a geocomposite, even sometimes a geotextile, it's not gonna be as, a hole is not gonna be as detectable as if it were on a floor where the head can kind of build up. So keep in mind that there's no industry standard guidance for minimum moisture content for ELL. When we come to the site, we make sure that the cover material is conductive enough, and we make sure that the subgrade is conductive enough, and then we just make observations. We document whether the geosynthetics look wet or dry, and it's just a visual evaluation. So we're only going to ask you to add more water if we have problems with surface desiccation, like we can't get the voltage readings with our probe on the surface of the material, or if we know that we have an issue with cover material or subgrade conductivity. So it's more of a design decision how much water you add before the test. Hopefully you have enough rainfall, but in some areas of the world, you can't count on that. So you do need to have a plan for how you're going to water that cover material if it's needed. So in a double line system, such as this example here, where you have a primary and a secondary geomembrane, you have to decide whether you're going to test one or both of these liner systems. And for testing the secondary, you want to make sure to perform the test before the overlying geosynthetics go down. So in this case, you'd want to test it before that GCL goes down, and especially before the primary goes down. It's not going to be testable once that primary geomembrane goes down. You want to make sure that you have an isolated condition if you're doing the cover testing methods for whatever geomembrane you're testing. So if you're testing the secondary after secondary drainage material placement, you need to make sure that secondary drainage material is isolated when you test it. And same with the primary drainage material when you're testing the primary geomembrane. Also keep in mind that if you are going to test the primary geomembrane, you need to make sure that the specs call out for electrodes under the primary geomembrane, because the testing company is going to need electrical access to that layer, or in this case, the secondary drainage material. So electrode sounds really fancy, but it's really just a bare solid copper wire per the recommendations of the ELL contractor. As a design engineer, you don't want to direct the electrode placement because every ELL contractor has the way that they like it done that they think is most effective. But it does need to state in the specs that it needs to be done, because if it's not in the specs, the contractor might forget about it. Now moving on to method selection. You can perform a bare geomembrane method, like you see on the left here, to make sure you find every little pinhole and knife slice, or you can perform the dipole method after cover material placement to make sure that you find the damage that's caused during cover material placement, or you can perform both to make sure you find both types of damage. So the method selection is going to depend primarily on your design goals, how much leakage is acceptable for your site. It's also going to be a function of project configuration that we're going to talk a little bit about in the next few slides. I just want to remind you that episode 1 of this series talked about all of the bare geomembrane methods, and episodes 2 through 4 went over the covered geomembrane methods. There's also a publication that was produced by ASTM, it's D6747, which is a guide for the selection of methods. And it goes over the advantages and limitations of both the bare geomembrane and covered geomembrane methods. All of the bare geomembrane methods have something that I call an equivalence clause, which basically means that all of the methods are effective at locating leaks. They all have to demonstrate that they can locate a 1 millimeter diameter hole in the lining system. But each one has advantages and limitations. So some are going to be more practical than others, and some are going to be more effective than others. So the ASTMs all state that an alternative standard practice should be allowed if mutually agreeable and warranted by the site conditions or clearly technical superiority or logistics or schedule. So as long as it's agreed by the project engineer, the ELL contractor can change which method they use. So it's sort of a safety clause in case we get a bare geomembrane method that is prescribed that isn't really going to work very well on a project, or site conditions change and that method is no longer practical. So speaking of bare geomembrane methods, where the ELL contractor can basically change the method as long as they can convince the site engineer that it's the right thing to do, all of those ELL contractors who use all of the bare geomembrane methods almost universally will all tell you that the best method is the water puddle method. And I think the main reason is that it can overcome those poor contact issues. If you have something like the arc testing and you have a hole on a wrinkle, it's just not going to pick it up. With the water puddle method, we can actually add additional water, take additional time. We could step on the geomembrane and encourage the water to get through that leak, and we can overcome a lot of those issues. The other reason why it's a popular method is that it's fast. It's faster than all of the other methods. In fact, I think it's probably easily 4 times faster than the arc testing method. So it's a very practical and effective test to perform. So the practicality and the effectiveness really make it the test of choice for large, somewhat flat geomembrane areas. I can tell you that it's difficult to perform on the slope, and in fact, it's not as effective on a slope. So basically for floor areas, anything up to about 3-to-1 slope, it's going to be the most effective and practical test. So the one exception to the water puddle method being the most practical bare geomembrane test is when the installer performs their own bare liner testing. And the thing is, the water puddle test is always a third-party test. Liner installers don't have water puddle method equipment. It's not commercially for sale. It's a little bit more difficult to operate. It's slightly tricky. It's subject to some site conditions. It's not a super simple test to do. However, arc and spark testing are very simple tests to perform. In fact, spark testing has been done by installers basically ever since the birth of that conductive geomembrane product. So it was always my belief that arc testing should be done, arc or spark, depending on the geomembrane, should be done by every single geomembrane installer. This would solve a lot of problems. So every square foot of liner that went down would be tested by the installer. However, for some reason, arc testing just hasn't caught on by installers. This particular photo is from a spark testing project. So this is a conductive back geomembrane. And I was hired as kind of a method auditor. So I went to site and I watched them do this spark testing method testing, and basically told the owner whether or not they were doing it right to help them make sure that the testing was done appropriately. So whether or not you have an audit of the test, I think it's a very practical way to go to have the installer check all of their work. So that way you don't have to mobilize a third party. It's a lot cheaper to do the testing. And the only real thing that can go wrong is that if the installer doesn't do it right. But if you have like a one-day audit of someone who used this test method as a third party, you can make sure that they're testing properly. And that way you get your entire installation tested while bare, so that you get the most sensitivity of all the methods, and you pay a lot less for that liner to be tested that way. If you have steep slopes, and I'd say anything greater than a 3-to-1, there's no way the water puddle method is going to work as well as one of the high voltage testing methods. It just, the water just doesn't want to go through that liner once you get certainly more than like a 2-to-1 slope. It just kind of sheet flows off the top. So anything with slopes, I would definitely be wary of someone who wants to do the water puddle method on it. So along those same lines, if you have something like a vertical wall, you definitely want the arc testing method. In the past, the water lens method was often used for testing vertical walls, and I'll tell you what, it It doesn't work either at all or barely at all, especially in comparison with the arc testing. The water just, even if you squirt it directly at the well, it does not want to go through, especially a small hole. So a note on special configurations and details. If you have an inlet or outlet structure as part of your facility, you really want to specify non-conductive materials for those things in order to thoroughly test them for leaks. If you have something like ductile iron or concrete that's conductive, you're only going to be able to test up to the geomembrane attachment to that feature. And I'll tell you, if you have a leak and you have a field fabricated boot on your project, it's your field fabricated boot that's leaking. It's the most likely place for leaks. So don't even bother with a test until you check your pipe boot. These boots are also difficult to test. So one thing you could do is specify spark testing of extrusion welds, which is something that's done by the installer. It's a different ASTM standard. And the other thing I want to talk about is tie-in areas. So this is especially for like landfill expansion cells. When you build a new cell and it ties into an existing cell, that tie-in area has been sitting there for sometimes an extended period of time. It tends to be dirty, wet. Sometimes it's a different type of liner. It's thicker or thinner. So it's really difficult to weld in these areas. When that tie-in seam that's made between the new liner and the old liner falls inside of the soil cover area, it's easy to test because it's covered, so you can test it while it's covered. So as long as there aren't excessive leaks there, it should be a really good, easy test to do. However, when that tie-in seam falls in your isolation area that's required for the covered geomembrane test, it's very often not tested. So some designers are now calling for arc testing of that exposed tie-in area as a companion specification to the dipole method on the covered areas of the liner. So here are some outlet details, both made of conductive material. One's metal and one's concrete. So these were both bare geomembrane projects where water puddle method was specified, but it's very difficult to test all the way up to this edge with the water-based method. It's a little bit more effective for the arc testing to cover up to the conductive feature. However, this conductive feature cannot be tested. So if you have a leak in a gasket, we're not going to pick that up. It's much better to use a plastic pipe boot detail instead of something conductive. So testing the plastic pipe boots can be tricky. It depends on whether the pipe boot is newly installed or dry before the test, or whether it's been leaking. If it's been leaking and there's a wet path to ground, then arc testing method is going to be really effective. If it hasn't leaked in the past, you want to cause it to leak. So something like a water puddle is okay, but it's best to actually cause hydraulic head across where there could be leaks, like this photo here, where the pipe boot penetration is completely submerged. This particular pipe boot, we were able to put a bladder in it to keep it from flowing to ground during the testing event. If the geomembrane is conductive back, then that doesn't matter so much. So it really depends on the type of liner and the configuration and the state that it's in during the test. Let's talk about tie-in testing. This particular voltage map here, we had the tie-in fall within the soil covered area. So we were able to pick up all the leaks on that tie-in seam. The only problem with this test is that it maybe took us about 4 hours to complete the test and several days to dig up all the damage. Once you find a leak, you have to dig it up, isolate it, check around it for additional leaks, and it's very difficult if you have multiple leaks in a tightly clustered area. It's a much cleaner test to actually test that tie-in seam while it's exposed. In fact, you can test the entire exposed area with the arc test, not just the seam. This is my favorite configuration for a landfill cell where they have this isolation flap up against the existing. And what we can do is we can test this area in here by flooding it with water while we do our dipole test. So as long as this area in here is wet, we'll pick up any leaks in this area. In fact, I just run my dipole instrument in this gap. As long as the feet are wet, it'll pick up any leaks in this area here. This map is from a project that was just like the photo that you just saw, where I was doing a dipole survey on the cover material, and there was a wide, maybe 10-foot wide area that was bare. They had flooded it with water. And see this leak signal here, you can start to pick it up. It was actually about at least 30 feet outside of the actual soil covered testing area. There was a big berm right here. So you can detect those leaks in that area as long as they're wet and leaking during the test. Some cross sections are difficult to test, like this one here, where you have an exposed primary geomembrane over a secondary geomembrane separated by only a geonet or a geocomposite, separated by something that's not conductive. So you aren't going to be able to test the primary geomembrane unless you have something conductive in the leak detection layer. So you can specify conductive back geomembrane as the primary geomembrane, and that conductive backing forms that layer. You can specify a conductive geotextile under the primary geomembrane, or if you don't want to do either of those things, you have to fill the leak detection layer with water. And by doing that, you're going to end up having to do a water dipole test, because you can't just fill the leak detection layer with water. It's going to float that primary geomembrane. You're going to have to put water on top of the primary. So you're going to have to do a water dipole test, which includes water management. It's a very sensitive test, so it's going to find every little pinhole, which means that it's very likely you're going to have to evacuate the water to fix whatever's found during the test. So you're going to have to decide whether you want a water dipole weighting survey or a filled pond test. Each of these has advantages and limitations, but just so you know, you can't easily test this liner cross-section unless you have something conductive between the liners. Now, if you can't hold water on this liner cross-section, for example, it's a landfill expansion with this cross-section, it becomes even more difficult to test because you need to have water in that leak detection layer. You need something conductive there. So when you're putting together your ELO method project specification, you want to think about how to test critical areas and what your design goals are for the project. You want to specify the method or methods, address the site and design specific isolation requirements for the chosen method, make sure to address moisture content issues, know your materials and your lining system, and know what it's going to take to have a good test with those materials. Outline the contractor support in the specifications, because they're going to have to provide a significant amount of labor, and also sometimes they're going to have to change their construction sequence depending on the test. So you want to make sure that's outlined in the project specifications. Recognize the need for electrode placement if you're testing the primary geomembrane of a double line facility. The ELO contractor is not usually responsible for providing the wire, although they are going to provide the wire layout for the project. Also, you really want to think about minimum qualifications for the ELO contractor. This could be number of years that the contractor has performed the testing method, could be number of projects, it could be square footage of projects, but it's basically a minimum experience level to make sure that you have a good testing company. Make sure that the company chosen is involved from the beginning with the project. So it's a really good idea to have a conference call ahead of time to go over the necessary site preparation to perform a successful test. And when in doubt, just ask. If you're putting specifications together, ELO contractors are always happy to help out, advising which methods are going to be most effective for your project and your design goals. According to Murphy's Law, whatever can go wrong will go wrong. And according to J.P. Drew, all liners leak. So even if we have a perfectly crafted ELO method specification and we've performed a perfect test and there's no actual holes in the lining system, your geomembrane can still leak. How is that even possible? Well, it can enter through anchor trenches or other unsealed locations. You can get stormwater going in between the liners and into the leak detection layer that way. But also vapor diffusion does happen through an intact geomembrane, just a very, very small amount. You can also have holes in the secondary geomembrane that allow groundwater to enter. So that's another reason why it's a really good idea to test the secondary geomembrane. But One of the phenomenon that we've seen throughout the years that really gives us trouble when we're trying to comply with an ALR is construction water trapped in the leak detection layer. So this is water that usually storm water that falls on the leak detection layer material during construction. And that granular drainage layer kind of holds onto the liquid for an extended period of time. Even if it doesn't rain very much during construction, sometimes we actually actively water that layer in order to enable testing of the secondary geomembrane. So the main check to find out whether something else is going on is to check whether the leakage measured is responsive to rainfall. So in 2020, I partnered with Larry Schilling to put together a case study of one of Casella's sites that had been experiencing this phenomenon. And we knew that the ELL method was applied successfully. We found very, very small damage in the liner in the primary. We fixed it. So we knew there weren't holes in the liner, but this landfill cell weeped for an extended period of time and even couldn't comply with the 20 gallons per acre per day allowable leakage rate. So I'm going to talk about that for a few minutes. It's one of the things that can go wrong, even if we do everything right. In order to understand the physics of this phenomenon, we have to look at a material property called specific retention. So let's look at a granular material that's been saturated. So we have soil particles, it's coated with a portion of water, and then there's some voids of air in the material. So this portion of water that sticks to the material basically forever at time equals infinity is what you call specific retention. Now, looking at this diagram, you civil engineers out there might think, well, that's field capacity. Well, actually, field capacity happens at time equals 0. So if you saturate a material, you let it drain under gravity, the portion of water that sticks to the material, that's going to be your field capacity. But let that same sample sit there forever, and eventually, after years, you will arrive at the value for specific retention. So how do we know this ahead of time about a material? Well, you put the sample in the lab after you saturate it, and you subject it to really high suction. So it's a standard suction and a standard temperature. The other thing about this property is that it's highly affected by temperature. So the water actually acts like the visual you can use is like an oil stuck to a surface. And when it's colder, the oil is more viscous. You heat up that oil and it becomes more liquidy and it starts to drain off of those surfaces. The same thing happens with water. So it will start to release more liquid as the temperatures go up and as time goes on. So if you look at this table here of the various materials, you can see something like sand, which is really problematic for these extended weeping periods of time. Sand has a specific retention of 3, but it has a field capacity of around 15%. So when sand gets saturated during construction, it slowly weeps until only 3% is stuck to that granular material. So the portion of liquid that's still stuck to the material, that's the specific retention. The portion that comes off is what we're measuring through the leak detection layer when the construction water is slowly weeping out. And that property is called specific yield. So to understand that relationship, you send a sample to the lab and you test for specific retention. You also test for porosity, and then that gives you specific yield. And that way you know how much water to expect from this layer. To illustrate the time scale of this phenomenon, the person who discovered this property set up a sand column test where he saturated sand, he put it in a column, and he measured how much liquid drained out. So he measured 40% in the first 30 minutes, then 18% more in the second 30 minutes. The additional third took 9 days, and the remaining last 10% took 2.5 years. So if you had a similar sample and you were measuring specific yield or the liquid that came off of that sample every day, that value would change and it would go up. and it would approach the ultimate value, which is our laboratory value, or specific yield at time equals infinity. So that laboratory value is obtained at a standardized temperature. It's subjected to extremely high suction, and they found that it has very good correlation to the ultimate value, or the forever value. When the yield of the material is changing every day, like that curve that we saw on the previous slide, you end up with a leakage that looks like this black line here. So the leakage will be high at the beginning and it will steadily drop, but then it will drop slower and slower as time goes on. So this blue line here is actually the measured flow, daily flow from the leak detection layer from the case study site. So it really wants to follow this sort of a trend like the black line here, except you see this bump up in the middle. Well, this red line up here, that's the average temperature. So you can see that we all of a sudden get a bump in leakage that's the same shape as those rising temperatures. And once the temperature goes down, the leakage picks up where it left off on that logarithmic curve. In conclusion, all liners may leak, but it is possible to install a geomembrane without any holes in it. However, you must use electrical leak location in order to achieve that. In fact, if you want any assurance that the geomembrane is going to perform as intended, you need to use ELL. Throwing it in the end of a project after issues are present, it's not 100% guaranteed to solve the problem. A good test starts with good project specifications, and the devil really is in the details. Very small testing details can be the difference between a successful project and a project that can't be permitted.
Thank you for attending our presentation.